Hello, welcome to the session on dynamical systems of this ConcurA workshop. So I am Aishwarya. I will be the chair for this session. We will have three talks. Sorry for the technical delay due to technical reasons. So during the talks, as you see the presentations, you can ask questions if you have any by using the question and answer feature of the Zoom, or you can also ask it in the comments. We can ask to the speaker after to the others afterwards. For the very first talk, it's on the orbit problem for parametric linear dynamical systems. We have Marcus here, who will be there to answer any questions and answers that you may have. So let's start with the first talk.
Hello, I'm Marcus Whiteland, and I'm presenting the paper The Orbit Problem for Parametric Linear Dynamical Systems. This is joint work with several researchers from the Technische Universität Dresden, the University of Oxford, and the Max Planck Institute for Software Systems under the guise of the Center for Perspicuous Computing. Before describing the topic of the paper, let me start with some motivation. In software verification,
Sorry, so there's a technical problem with the sound. I think we will restart the video with, sorry for that. We will restart it once again.
have x equals 2, y equals 1, and z equals 0. We now define a dynamical system according to this. Hello, I'm Marcus Whiteland, and I'm presenting the paper The Orbit Problem for Parametric Linear Dynamical Systems. This is joint work with several researchers from the Technische Universität Dresden, the University of Oxford, and the Max Planck Institute for Software Systems under the guise of the Center for Perspicuous Computing. Before describing the topic of the paper, let me start with some motivation. In software verification, we are interested in correctness of programs, like the one pictured here. In order to analyze a program, we might consider the building blocks of the program itself. The idea is that if the smaller parts work correctly, then so does the whole program. Here we have some conditional blocks and some loops. When considering a loop, a natural question is, does this loop halt? Let's have a closer look at a simple while loop and how one would model it as a dynamical system. We have three variables, x, y, and z, which are initialized as 1, 2, and 3 respectively. We then enter a while loop, where we see that the variables are updated by fairly simple operations. The loop halts if we simultaneously have x equals 2, y equals 1, and z equals 0. We now define a dynamical system according to this. First, we have an initial point, which is determined by the initial values of the variables. We then define an update function. By inspecting the loop, the update can be seen to be a linear map, which we can express as a matrix as so. The next state of the system is obtained from the previous state by applying the matrix M. Starting from the point x0, x1 is obtained from x0 by applying M to it. x2 is obtained by applying M to x1, which equals m squared applied to x0. We can carry on so that the nth term of the sequence is just the m to the n applied to the x0 point. Now, the loop holds if there exists an n such that when m is applied n times to the initial vector x0, we get the target vector 2, 1, 0 in this case. We may formulate the problem of the loop halting in terms of the so-called orbit problem in linear dynamical systems. You are given a starting point x in R to the d and a linear update map m. You then get an orbit by applying m on x indefinitely. In the picture we have the matrix and the initial point. Now the second point in the orbit is just m of x, so we get another point in the plane. We get m squared of x, m cubed of x, and so forth. Now we add a target point into the mix and we ask whether the orbit contains this target point y. This is the orbit problem for linear dynamical systems. So one could keep on going and see that probably in this case the target cannot be reached, but you don't need to guess. This is an actual theorem that this problem is decidable when x, y, and m contain algebraic entries. In fact, it is decidable in polynomial time when x, y, and m contain rational numbers. So, the Cannon-Lipton theorem shows that it is decidable whether these kinds of while loops halt or not. But these are quite simple. Usually one would have input so that the initial point depends on the input. We might even have that the update map depends on the input, and even the target vector might depend on the input. Now, for any fixed input, assuming it's rational or algebraic, the loop halting problem is still decidable by the Cannon-Lipton theorem. But halting depends on the input, and you might have halting for different n for different inputs. The problem we study in this paper is motivated by this more general question. Does there exist input a1 to ak such that the loop halts? Namely, does m to the n applied to x equal y when m, x, and y are initialized according to the input? We now formulate the problem precisely. For some notation, we let q of z1 to zk denote the set of rational functions in k variables. One can think of them as functions obtained by the basic operations multiplication, division, addition, and subtraction on the variables and the rational constants. The setup of the problem is as follows. We have initial vector x, which is a d-dimensional vector whose each coordinate is given by a rational function from q of z1 to zk. We have the update matrix M, a d by d matrix whose entries are rational functions in q of z1 to zk, and finally a target vector y, which again has rational function entries. We then want to know whether there exists an instantiation of the variables such that the corresponding target vector is in the orbit of the induced dynamical system. In other words, does there exist a vector a in R to the k and an integer n such that the target vector equals m to the n applied to x with this instantiation of the variables? For a geometric view on the problem, consider the following setup. We have one variable s which can be taken to be any real number. We have the initial vector x which depends on s, and we have the update matrix again depending on s, as seen here. In the picture we have a part of the range of the initial vector. It is the vertical blue line. Mapping x by m, we get part of the range of the second point in the system. It is this parabola opening to the right. Mapping again by m, we get the range of the third point in the system, which is now m squared of x. And continuing, we get the fourth and the fifth and so forth ranges. We then add into the mix this target vector y depending on s, and the range of y is this red circle in the picture. Let me now state the results of the paper. Recall the problem statement. Our initial and target vector as well as the update matrix have rational function entries. We want to know whether there exists an instantiation of the variable such that the induced target vector is in the orbit of the induced dynamical system. Our main theorem has some good news and some bad news. For univariate systems, i.e. there is only one variable, the parametric orbit problem is decidable. For multivariate systems, i.e. there are at least two variables, the parametric orbit problem is Skolem hard. Now, the second point might not be familiar to everyone. The Skolem problem is a decision problem which is not known to be decidable or undecidable. The second point says that if the parametric orbit problem is decidable, then one could decide the Skolem problem, which again is currently an open problem. Let me describe this problem next. Skolem's problem can be expressed as a halting problem on while loops with linear updates. The structure of the loop is exactly the same as we discussed previously, except that the loop guard is different, and here we do not have any input. Here the loop halts if the inner product of the loop variable vector with a fixed vector u equals 0. Geometrically, this means that the loop halts if there is a point in the orbit that hits the hyperplane defined by the vector u. This is a subspace of dimension d-1 if there are d variables. Here are some quotes testifying the situation of the problem. The computer scientist Richard Lipton states it as a mathematical embarrassment. And Terence Tao, a famous mathematician, says, "It is faintly outrageous that this problem is still open. It is saying that we do not know how to decide the halting problem even for linear automata." Now, the Skolem problem is usually stated as a problem on zeros of linear recurrence sequences. This has been studied since the 1930s. Here is a picture of Thoralf Skolem, who studied the zeros of linear recurrence sequences in the 1930s. The problem is known to be decidable for instances with dimension at most 4, when we assume that the entities involved are real algebraic numbers. Here the dimension refers to the number of loop variables in the context of while loops. It is open for systems with dimension at least 5. Now that we know what the Skolem problem is all about, I will sketch the hardness proof for the parametric orbit problem. Recall that for two parameters, the problem is to decide whether there exist values of parameters a1 and a2 such that the induced target vector is in the orbit of the induced dynamical system. We show that if one can solve the bivariate orbit problem, then one can solve Skolem's problem for dimension 5. Recall again that the Skolem problem asks, given vectors u and x and a matrix M, whether there exists n such that u times m to the n of x equals 0. Now, a hard case of Skolem, a one that is not known to be decidable, can be written as an exponential polynomial like so. So the nth term has a closed form, and lambda and gamma are complex numbers with equal modulus. One can rewrite this as follows, as the imaginary parts always cancel out. The constants here are real algebraic numbers. We then construct an instance of the parametric orbit problem. We construct the initial vector and the update matrix that somehow encode these eigenvalues. So n will have lambda and gamma as eigenvalues. However, n and x will be constant. The target vector will be the only entity which varies according to the input parameters. We then construct a 2D algebraic target set in ambient dimension 4. The algebraic set is defined by two polynomial equalities, so it has dimension 2. If you don't know what the dimension of an algebraic set is, don't worry, it's not important. Now, the first polynomial equality here is taken from the form of the Skolem instance. So the coefficients a, b, c, d, and e are exactly the same as in this form here. The second polynomial equality comes from the assumption that lambda and gamma have equal modulus. So when we have x equals the real part of lambda to the n and y equals the imaginary part of lambda to the n, similarly z equals the real part of gamma to the n and w equals the imaginary part of gamma to the n, then we must have x squared plus y squared equals z squared plus w squared. Now, a further step is to show that this algebraic set can be expressed as the range of a bivariate target vector. I'm cheating a bit here. The target set is actually a finite union of such target vectors, and these target vectors have algebraic functions as entries, but let's not worry about that here. Now, with these ingredients, we show that our instance of the Skolem problem is positive if and only if the constructed instance of the parametric orbit problem is a positive instance. This concludes the proof sketch. I refer to the details in the paper for the interested audience. Now that we have the bad news out of the way, let's turn to the good news. I'll now talk a bit about the univariate case and give some idea why it is decidable. Recall that in this case we have a single parameter and we want to know whether there exists an integer n and a real number s such that m of s to the n times x of s equals y of s. To show decidability, we have the following main ingredients. First of all, we use the Jordan normal form of the update matrix. Now, this is a known technique when considering rational constant matrices, but here we need to consider matrices consisting of rational functions. I'll explain a bit how this works later. Second, we use a heavy dose of number theory. I mention here that for constant matrices, we need to solve instances of the Skolem problem. To do this, we employ powerful techniques from transcendental number theory. And for those who know such results, I mentioned Baker's theorem for linear forms in logarithms and p-adic versions of it. These methods are fortunately already known in the literature. When we have parametric matrices, however, we need to dive into the world of algebraic curves, and we use some recent results from that topic. I will explain this also later on. Let's first discuss the Jordan normal form. The Jordan normal form, or Jordan decomposition of a matrix, is a factorization result. It says that any matrix M can be expressed as the matrix product of this form. M equals S inverse times J times S, where S is an invertible matrix, and J, a so-called Jordan matrix, is a block diagonal matrix with Jordan blocks on the diagonal. Each Jordan block, i.e. one in a red rectangle, has a constant diagonal, and the superdiagonal consists of ones. Everywhere else we have zeros. The lambdas on the diagonals of the Jordan matrix are the eigenvalues of the matrix. Now, if M is defined over a field K, then the matrices S and J are defined over an algebraic field extension of K. Now, our M is defined over the field of rational functions. This means that S and J are defined over some algebraic function field, i.e. have algebraic functions as entries. An algebraic function is a meromorphic function that satisfies a polynomial relation with its argument. So P of Z and F of Z equals 0 identically for some bivariate polynomial P. The problem statement involves taking powers of the update matrix M. We might recall from linear algebra that it is convenient to transform the matrix into a diagonal form if it is diagonalizable. The Jordan matrix is almost in diagonal form, and the decomposition of M into Jordan normal form allows to simplify the powers of M, as can be seen here. Now, the powers of the Jordan matrix are easy to compute. I'll show you later on. So now we would wish to replace M of t with the corresponding Jordan normal form instantiation. But recall from the previous example that we have some problems with instantiations, and that the elements of J and S are algebraic functions. Luckily, it can be shown that for all but finitely many choices of t, we have this equality. Furthermore, these finitely many exceptions can be checked separately, as they are instances of the original constant orbit problem. So we can slightly modify the univariate orbit problem. We have J, a Jordan matrix, and the initial and target vectors x and y all having univariate algebraic function entries, and we ask for an instantiation of the variable such that the induced target point is contained in the orbit of the induced dynamical system. Okay, so let's have a look at what kind of equations we obtain from this form of the problem. Now, looking at the power of the Jordan matrix, it is quite simple. Now, we get a system of equations for each of the Jordan blocks. Now each Jordan block has a fairly nice closed form. So, from each Jordan block and the corresponding part of the initial vector, we get a system of equations as follows. Now the proof of the decidability is a large case analysis depending on the structure of the Jordan matrix. For simplicity, I will explain the case where we employ some results from algebraic geometry. For this, we notice that each block gives this kind of an equation: lambda I of s to the n equals gamma I1 of s, where lambda I and gamma I1 are algebraic functions. Keeping in mind these simple equations, I recall a theorem of Bombieri, Massa and Zanier. The setup is as follows. Assume you have an algebraic curve in c to the d, and assume that the coordinates on the curve are such that any product of the coordinates is not a constant identically. For example, you can consider the straight line defined by z equals y plus 1 equals x plus 2 in the ambient dimension 3. Now, assuming that we have such a curve, there are only finitely many points on the curve such that two different products of the coordinates equals 1. Furthermore, one can effectively find these points. Okay, so this looks like a crazy theorem, and how on earth would one apply this to our problem? I'll briefly explain this. Recall that we have our system of equations. Let's assume that we have two such equations. Now we construct a curve in ambient dimension 4 whose coordinates are parametrized using these functions. Now if the functions involved are such that no product of them gives a constant function, then the curve satisfies the assumptions of the Bombieri-Massa-Zanier theorem. It follows that there are only finitely many s for which there are two products of the coordinates that equal 1 simultaneously. Now we may take these two products. Now we can find these points and check whether we get a positive instance of the induced orbit problem. We know that there can only be finitely many s for which this holds. Okay, that's all I wanted to say about the paper. As a recap, recall that the parametric orbit problem asks whether given initial and target vectors consisting of rational functions and an update matrix also consisting of rational functions, we ask whether there exists an instantiation of the parameters such that the induced target vector is in the orbit of the induced dynamical system. We show that the problem is hard for at least two parameters, and it is decidable for a single parameter. The hardness result was a reduction from the Skolem problem. The Skolem problem has been used as a source of hardness in the literature for quite some time now, and is considered a well-known and established problem, not known to be decidable or undecidable. The decidability result was obtained by deep results from the field of algebraic geometry. The theorem of Bombieri-Massa-Zanier is one that you might want to keep in mind when dealing with such problems. The theorem is much more general than how we've used it here. Namely, we only used a baby version of it. I'd also like to mention that here we essentially only considered vector reachability. The results, however, can give some stronger results, but this is a topic of future work and another paper. Thanks for your attention, and I look forward to answering any questions you have about the topic.
So thank you for the very nice presentation. Now it is time to ask questions. We don't have any questions at the moment in the chat or in the question and answer. So I encourage you all to please put them on the chat. And while they type it, maybe I have a question. So you consider point-to-point reachability, right? Like it's a vector to a vector. Can you consider a region to another region? Does it just
so this region to a region would be, I suppose it would fall into the several variables case, but this is already quite hard.
Why would it? Because anyway, in the matrix, we have only one variable, but just to represent the source vector instead of a single vector, it may be a set of vectors given by a region and the target vector also.
Yeah, so I suppose there you have this kind of, you could add somehow an independent variable describing these initial states or the target states, and then I suspect that it would get hard again because of kind of a second source of freedom.
I see. So I'm still encouraging people to ask questions. So while they are doing it, I'll ask one more question. So typically we can think of these matrices as transformation matrices of some finite state systems, right? Like Markov chains, for example. So so since we have only a single matrix, it would correspond to a unary alphabet in some sense. And then you're looking at reachability. So what if we have let's say binary alphabet? We have 2 letters. So essentially that will correspond to having 2 matrices, both of them on the same variable, single variable. Is it any more difficult, or does it just straightforward does your result extend straightforward to this case?
So I think you're already getting to dangerous waters because of the mortality problem, which is undecidable when you have several matrices. So yeah, even for constant matrices, if you have several matrices, it's already a difficult or undecidable problem. And even in dimension 2, it's not known whether point-to-point reachability is decidable.
Okay, thank you. That's very interesting. So it's really the limit of what can be decided. Okay, thank you. So I don't see any questions at the moment. So maybe you can take more during the. So if somebody has a question later during the gather town or something, so maybe we can go to the second talk. We have Anish Shetty on the panel to answer any question and answers that you may have. So feel free to ask them on ask comments while the talk is going on, or you can also use the Q&A feature of the Zoom. So this talk is on deciding polynomial termination complexity. Oh, so this is a different talk. This is not the, okay. So this is the third talk, sorry. So there is a swap in this thing, sorry. So, okay, so now then we have Michael and Antonin also probably will join. Tony will also probably join us on the panel. So this talk is on deciding polynomial termination complexity for vast programs. Okay, so maybe you can play the video.
Hello, my name is Tony Kuchera, and I am presenting a joint work with Michal Ajdarov on deciding polynomial termination complexity for vast programs. Let me start by introducing our computational model. A vast game is essentially a finite state directed graph where the control states are split into 2 disjoint subsets of demonic and angelic control states. We use circles to denote demonic states and squares to denote angelic states. A bus is equipped with a finite collection of counters initialized to some non-negative values, and the current counter values are modified by performing transitions. So in every control state, the responsible player selects an outgoing transition, and the current counter values are updated by the associated counter update vector. So in this case, we have just 2 counters, and by performing this transition, the first counter is increased by 7, and the second counter is increased by 5. A computation terminates when one of the counters becomes negative, and the aim of player Demon is to prolong the computation as much as possible, while player Angel aims at shortening the computation. To capture this objective formally, we define the notion of termination value and termination complexity in the following way. So first, consider some initial configuration PV, so P is the initial control state and V is the vector of initial counter values, and consider a pair of strategies for the two players, so for the player Angel and Demon. And let us consider the maximal computation initiated in PV obtained by applying the two strategies. So in principle, this maximal computation can be finite or infinite. The termination value of PV, denoted by T-val of PV, is intuitively the length of the maximal computation obtained from PV if both players play optimally. So more formally, we need to show that this usual sub-inf sub equality holds, and this equality formally defines the termination value. Termination complexity is a function which to every n assigns the maximal termination value of a configuration where all counters are initially bounded by the n. So intuitively, this n is a bound on the input size represented by the counters, and this function L tells us what's the length of the maximal computation for all inputs whose size is bounded by the n. Termination complexity can also be seen as an analog of the standard time complexity used in program analysis. We also have an analog of space complexity, which is called counter complexity. It is defined in pretty much the same way as termination complexity. The only difference is that instead of measuring the length of the computation, we look at the maximal value of a given counter, small c, along a computation. So formally, a counter complexity is a function which to every n assigns the maximal c-val of a configuration where all counters are initially bounded by the n. The existing works about termination complexity and counter complexity study questions related to the asymptotic growth of these two functions. For example, we may wonder whether the termination complexity is finite for all arguments, and if it is the case, we may further ask whether it is linear or cubic or at most exponential, and so on. But before giving a more detailed overview of the existing results, let's have a look at some motivating examples. Let us first consider this simple program. It starts by inputting a non-negative integer value I and continues by executing these two nested while loops driven by the variables I and j. And our aim is to determine the time complexity of this program. This can be achieved by constructing a VAS model for this program and analyzing its termination complexity. Of course, there are several obstacles. First of all, a VAS cannot test a counter for 0, which means that we cannot faithfully model this test. And furthermore, we cannot faithfully model the assignment because there is no instruction for transferring the content of one counter into another counter. The first problem is overcome in the usual way by replacing conditionals with non-deterministic choice. The non-deterministic choice will be demonic. And the second problem can be overcome by modeling the assignment using a third auxiliary counter, which is first set to 0 together with the j, and then in this while loop we keep decrementing the I and incrementing both j and aux, and after that we restore the original value of I by transferring the content of aux back to the I. And now for this program we can construct the VAS model simply by replacing these conditionals with non-deterministic choice. In this way we obtain the VAS model shown here. It has just 5 control states, all of them are demonic, and this VAS over-approximates the behavior of the original program, which means that the execution of the program for a given input value n corresponds to a certain computation initiated in this control state where all of the 3 counters are initialized to the n. And hence, an upper bound on the termination complexity of this VAS is a valid upper bound on the time complexity of the original program. As we shall see, the termination complexity of this VAS can be analyzed efficiently, and it is actually quadratic, which means that the time complexity of the original program is at most quadratic. And a closer look at this program reveals that this bound is in fact optimal. Our next example illustrates the use of angelic control states. So our program again starts by inputting a non-negative integer value I, and then there are three other variables that are set to 0 initially. Then the program executes some if statement. The condition is actually not so important because in the end it will be again modeled by a demonic choice in the VAS model. And depending on this condition, the program continues by executing one of the two branches. In each branch, the values of the three variables are modified in some way. And when this if statement is completed, the program or the controller of the program continues by executing this choose statement. So now the controller may choose to execute either this or this statement, and the aim of the controller is to keep the value of z as small as possible. Now the question is, what is the asymptotic value of z achievable by an optimal controller? I mean, what is the value of z as a function of the input size? And using the results of this paper, this question can be answered fully automatically. And it follows that the value of z stays linear in the size of the input value. Now, I hope you are more or less convinced that it makes sense to consider problems related to algorithmic analysis of termination complexity and counter complexity in VAS games. So let's see what has been proven in previous works. For completeness, let me start with the very basic questions where the answers follow easily from well-known results. So the first question is whether we can decide whether the termination complexity is finite for all n. For purely demonic VAS, where all control states are demonic, one can easily observe that the termination complexity takes the infinite value for some sufficiently large n if and only if there exists a self-covering sequence or self-covering computation of this form, where this u is larger than v. And the existence of such a self-covering sequence can be decided in polynomial time simply by Cross-Archer-Sullivan algorithm. For VAS games, where we have both angelic and demonic control states, the answer is also simple. The crucial observation is that if the player angel has some strategy, sigma star, such that every computation initiated in an arbitrary initial configuration is finite when the angel commits to the strategy sigma star, then the player angel also has a counterless strategy with this property. A counterless strategy is a strategy depending only on the control state. And this means that the problem belongs to the class NP because we can simply guess an appropriate counterless strategy, implement this into a given VAS game, and thus obtain a demonic VAS where the algorithm of the previous point can be used. And one can show that the problem is also NP hard. So in fact, the question is an NP complete problem. Another natural question is, how fast can the termination complexity grow, assuming it is finite for every n? And by using the classical results of Maya and Maya, one can easily show that even for purely demonic VAS, the termination complexity can grow very fast, which means that it can grow as fast as an arbitrary function in the standard hierarchy of fast-growing functions, which is recalled at this slide. And not so surprisingly, we need more and more counters to achieve this growth. Here we have a full summary of results that have been proven for purely demonic class. First, the problem whether the termination complexity of a given demonic class is linear is solvable in polynomial time. And if the termination complexity is not linear, then it is at least quadratic. The polynomiality of termination complexity, that is the question whether the termination complexity is asymptotically bounded by some polynomial, is also solvable in polynomial time. And again, there is a kind of gap saying that if the termination complexity is not polynomial, then it is at least singly exponential. The question whether the termination complexity of a given demonic class is bounded by a polynomial of a given degree k is solvable in polynomial time, assuming that the graph, the underlying graph of the demonic class, is strongly connected. And furthermore, if the termination complexity is polynomial, so if it is bounded by some polynomial, then the degree of the bounding polynomial, I mean the least degree of a bounding polynomial, is computable in polynomial time. In the same paper, it has been conjectured that this result actually holds for all demonic classes, regardless whether or not they are strongly connected. As we shall see, this conjecture is not true. Finally, there is a result saying that the problem whether the termination complexity of a given demonic class belongs to a given level of the Grzegorczyk hierarchy, GK, is solvable in polynomial time. And furthermore, if the termination complexity does not belong to the class GK, then it grows at least as fast as the generator fk plus 1 of the next class gk plus 1. These results are rather encouraging. The considered problems are certainly not trivial, but still they are solvable efficiently in polynomial time. For vast games where we have both demonic and angelic control states, the complexity becomes somewhat worse. First, the problem whether the termination complexity of a given vast game belongs to a given level of the Grzegorczyk hierarchy is NP complete. Here, the main argument again relies on revealing the special role of countless strategies. More precisely, if the player angel has some strategy pushing the termination complexity to the class GK, then the player angel also has a countless strategy with this property. In the same paper, it is also noted that these observations, and in particular the one about the countless strategies, are no longer valid for the polynomial hierarchy. Even the question whether the termination complexity of a given vast game is at most quadratic is shown p-space hard. The decidability of this problem is left open in this paper. But it is also noted that the player angel cannot commit just to countless strategies. The player needs to take into account the current values of the counters. Now we are ready to formulate the main results of our paper. These results give a full classification of the computational complexity of the problems of asymptotic analysis of termination complexity and counter complexity in demonic vast and vast games with respect to the polynomial hierarchy. For demonic vast, we refute the conjecture of Florian Zolleger and show that for a general demonic vast, which is not necessarily strongly connected, we have the following. The problem whether the termination complexity is asymptotically bounded by n to the k is solvable in polynomial time for k equal to 1, and for larger k at least 2, the problem is co-NP complete. The problem whether the termination complexity is asymptotically bounded from below by n to the k is in polynomial time for k at most 2, and for larger k it is NP complete. And the question whether the termination complexity is asymptotically equivalent to n to the k for a given k is in P if k is equal to 1, co-NP complete if k is equal to 2, and DP complete for k 3 or larger. And the same results hold also for the counter complexity. Our second theorem gives the same sort of complexity classification for VAS games. So the theorem looks similarly as the previous one, only that the complexity classes are higher. In the rest of this talk, I present at least some of the main ideas and proof techniques behind theorems 1 and 2. I concentrate on the analysis of counter complexity instead of termination complexity because this problem is in fact more general. The questions about termination complexity can be easily reduced to the corresponding questions about counter complexity simply by adding a new fresh step counter to a given VAS, which is incremented by every transition. Hence, the counter complexity of the step counter is the same thing as the termination complexity of the original VAS. Let me start with theorem 1, which applies to demonic VAS. And let me first recall the result of Florian-Zolliger applicable to strongly connected demonic VAS. The theorem says that for every counter in a strongly connected demonic VAS, the corresponding counter complexity is either asymptotically equivalent to a polynomial of some bounded degree k, or the counter complexity is at least singly exponential. And it is decidable in polynomial time which of the two possibility holds, and in the first case, the k, the degree of the polynomial, is computable in polynomial time. This theorem can be visualized as follows. So this box represents the only strongly connected component of a given demonic VAS. The counters are initialized to the n, and here we have the vector describing the asymptotic growth of the first, the second, and the third counter. A simple observation is that the three counters can actually be pumped to the corresponding asymptotic values simultaneously. This is because we can imagine that we initially divide the n by 3 and use the first third of the n to pump the first counter to the value which is still asymptotically equivalent to n squared. Then the second third is used to pump the second counter to the value asymptotically equivalent to the n. Well, this computation can consist of 0 transitions. And the last third is used to pump the last counter beyond the singly exponential value. Also note that these vectors do not represent some kind of pumpable patterns because the actual value of the second counter in this simultaneously pumping computation may actually decrease. So it is still asymptotically equivalent to the n, but it can be strictly smaller than the n. Now, if we have a general demonic VAS, which is not necessarily strongly connected, we can decompose the VAS into strongly connected components and consider or compute the duck of these strongly connected components. And then we can analyze the asymptotic growth of the counters for each of these strongly connected components independently. However, there are several issues. The problem is that the initial counter values in these non-top components can be asymptotically larger than the n, which means that the theorem presented at the previous slide doesn't apply because it assumes that the counters are initialized to the n. So we start by generalizing the theorem of the previous slide so that it is applicable also to the situation when the initial counter values are not just n, but n to the k. The k doesn't have to be the same for all counters. Each counter can have its special key, but still the initial counter values must be bounded by a polynomial. So when the initial counter values are bounded by a polynomial in n, we can analyze the asymptotic growth in every counter. And the length of the computation, which simultaneously pumps the counter values to their asymptotic bounds, is at most singly exponential in Vn. And this exponential bound on the length of the pumping computation allows us to handle the counters that are pumped beyond singly exponential values. Because since this counter can be pumped to something which is at least singly exponential, we can assume that it is sufficiently large so that it does not block the pumping computation for the other counters. So we can technically abstract this counter away, and this is denoted by the star in here. So what we technically do, we modify the VAS so that it does not change the value of the last counter. And since the length of the pumping computation is singly exponential, we can assume that the value of the third counter is sufficiently large so that it provides a sufficient credit not only for this exponentially long computation, but also for each of the constantly many exponential computations performed in the components below this one. Also observe that different paths in this duck may produce different vectors of initial counter values, and we need to analyze each of the vectors independently. And in general, the total number of such initial vectors can be exponential, so computing the whole structure takes exponential time. Still, if we wish to decide whether the asymptotic value of, let's say, the first counter is at least n cubed, it suffices to guess an appropriate path in this graph and verify that the associated growth of the counters, which is unique, is such that the first counter is indeed pumped beyond n cubed. In this case, the witness would be this path. And this leads to the NP upper bound presented in theorem 1. The other bounds are obtained similarly. Proving theorem 2, the results about VAS games, is a bit more demanding, and here new concepts and new proof techniques are required. As we already noted, the player angel, who aims at shortening the computation, can no longer commit just to countless strategies, but still we can prove that he can commit to a very special type of strategies we call locking strategies. And a strategy is locking if the following property holds. Whenever an angelic control state is visited for the first time, the strategy picks one of its outgoing transitions and locks the transition, which means that whenever the state is revisited in the future, the locked transition must be used. So, as the computation proceeds, the underlying VAS game becomes more and more demonic. And this gradual change of a VAS game into a demonic VAS is described by a suitable structure which we call locking decomposition, and it can be considered as a generalization of the standard duck decomposition for demonic VAS we used in the previous construction. And finally, we show that the player angel can commit even to a special type of locking strategies called simple locking strategies, where the selection of the lock transition depends just on the history of components in the locking decomposition visited by a computation. And this result allows to construct an alternating polynomial time algorithm that goes over the locking decomposition and searches for a suitable simple locking strategy. And since alternating polynomial time is the same as p-space, we obtain the upper bounds of theorem 2. An interesting direction for future work is to extend the presented results to stochastic extensions of vector addition systems, such as VAS MDBs or even VAS stochastic games. Positive results achieved for these models might provide a new and potentially powerful basis for probabilistic program analysis. This is the end of my talk. Thanks for your attention.
Thank you for the presentation. So we already have one question in the Q&A. So this is from Slavak Lasota. So he asks in the theorem 1, where we look at the complexity and say that if k equal to 1, it is it's p, k equal to 2, it is coin p, and so on. He asks if k is not fixed but given as part of input, what would be the complexity of the decision problems? So on the panel, we have Michael. Tony has some difficulty getting promoted to panelist. So maybe Michael can answer this.
Okay. So the question is, if we don't know the k, if what is the complexity of computing it?
We do know the k, but k is given as part of the input. It is not fixed beforehand. It's also part of the input.
Yes, that's what we. Then the complexity is the same as in the presentation. We assume it is given as the input in the complexity which were presented. So it doesn't. We don't assume it's fixed. We assume it's given as the input along with the rest.
I hope I got the question correct, Slavik. If you want, you can type again, or if you want, we can try to unmute you. Yeah. I think this is what he wrote in the Q&A. If you would take a look. Yeah. So thanks for answering that. Are there any other questions meanwhile? Okay, so then I propose that we move on to the next talk, sorry, because of lack of time. And thank you for answering again, and probably people can ping you again during the gather town or later. So thank you. Now, let's go to the next talk finally, which is order reversal. The talk is on scope-bounded reachability in valence systems. And we have Anish Shetty on the panel to answer the questions. So as before, please do type in your questions in the Q&A or on the chat as you get them. You don't need to wait until the end. So over to you, over to the presentation.
Hi everyone, I am Anish and welcome to our talk on scope-bounded reachability in valence systems. We will first describe what valence systems and graph monoids are. Next, we will motivate our definition for scope-bounded computations in valence systems. Finally, we will state our scope-bounded reachability problem in valence systems and describe our algorithm and a brief overview of its proof. A valence system can be intuitively described as having a finite control with states Q and a monoid that is used to describe the transitions. The transitions between states are labeled by the generators of the monoid. The configuration of the valence system at any point during a run is simply the state we are at and the concatenation of all the elements of the monoid read until then. The acceptance condition that we consider is when the word reached till the final state can be reduced to an empty word using a congruence relation described on the monoid. Since the congruence relations and types of monoid can be very vast, we focus on an interesting subclass of monoids, namely graph monoids. Graph monoids are described by an undirected graph with possible self-loops. Each node in the graph is a counter symbol. The alphabet of the monoid has a push and a pop operation for every node. The monoid elements that label the transition are all the words that can be formed by these operations, and these can be reduced under the congruence relation as described by the graph. The congruence relation is defined by these rules. The first rule is the push and pop operation. Every push followed by a pop can be reduced to an empty word. Second is the independence relation. If two nodes in the graph have an edge, then any operation of one node can commute with any operation of the other node. In case of a self-loop, it means that a pop followed by a push can be commuted and then by using the first rule be cancelled out. Intuitively, they are parts of independent storage. Now we give some examples of storage mechanisms. This is a single pushdown with three symbols, since none of the symbols can commute with each other, so the accepted word will be perfectly parenthesized. This again is a single pushdown, but with the additional property that a pop followed by a push can now be cancelled. Here, all three symbols are pairwise independent, so these are three independent counters. Since a pop before push won't be reduced, these are natural number counters. These are three independent integer counters. This one is a two push down, each with two symbols. One stack is of A and B, the other stack is of C and D. Notice that any sequence of A and B can be commuted across any sequence of C and D, which makes them behave as independent stack. Thus, graph monoids can model natural counters, integer counters, their stacks and combinations. Graph monoids cannot model queues or higher order stacks. Now we will see what it means for a computation to be dependent and context decomposition in case of valence systems. A computation is dependent if all the distinct symbols in the computation are pairwise dependent, which means that they do not have an edge between them in the graph. In case of multi-pushdowns, context decomposition is fixed since dependence forms an equivalence class. This is not the case with graph monoids in general, and it can yield different context decompositions for the same word. Thus, we describe our canonical context decomposition inductively. The first context is the maximal dependent prefix of the word. Inductively, the ith context is the maximal prefix of the word w dash which is remaining after removing the first I-1 context. With this, we are ready to motivate and define scope-bounded computations. First, let us look at scope-bounded computations for multi-pushdowns. A computation in a multi-pushdown is k-scope bounded if and only if, for every stack, every push symbol is popped within k revisits to that stack. Note that we do not bound the number of visits to the other stacks in between these. In terms of context, if there is a reduction of the computation to an empty word such that between every push and its corresponding pop symbol, according to this reduction, there are at most k-1 contexts of the stack to which this operation belongs. In the case of our diagram, the computation is 3 scope bounded. Observe that this describes a potentially long-range property of the word. For example, the computations shown on the slide is 2 scope bounded for all m and n greater than 0, where a, b, and c are 3 independent stacks. A property of multi-pushdowns is that the relation dependence forms an equivalence relation on the symbols. That is, a symbol is a part of one and only one stack. This is not true in case of general graph monoids. Consider the monoid on the slide. Here, A and B are independent and can commute with each other, but neither of them can cross the symbol C to commute with the symbols on the other side. To handle this and get an equivalence relation, we define weak dependence on the symbols as well as context. Distinct symbols U and V are weakly dependent if there is a path between them in the complementary graph. Weak dependence is an equivalence relation on the symbols and by extension on context as well. Intuitively, each weak dependent class is treated as an independent stack. For multi-pushdown, weak dependent classes are exactly the different stacks. With this, we can now define scope-bounded computations in valence systems. A computation W in a valence system with a graph monoid is k-scope bounded if and only if W can be reduced to an empty word and there is a greedy reduction of W to the empty word such that for every Wx that cancels with a Wy, under this reduction there are at most k-1 context between Wx and Wy that belong to the same weak dependent class as that of Wx and Wy. Again note that we do not restrict the number of contexts of the other weak dependent classes. A greedy reduction is the one where we first start by saturating the reduction rule of push followed by a pop to empty and pop followed by a push to empty if a self loop is present until all the contexts become irreducible. Now we can define the bounded scope reachability problem in valence system on graph monoids and state our main result. Given a finite graph gamma, a valence system over the monoid generated by gamma, and a scope bound k, we want to decide if there is a run from an initial state to the final state using some word w in the monoid such that w is k scope bounded. Our main result is that bounded scope reachability is in p-space in K, the valence system, and the graph for all graph monoids. Now we will see a brief outline of the proof method. First, we represent all contexts in their block decomposition form. Then we upper bound the number of blocks that each context can be reduced into. Next, we move from words to block abstractions. These will store all possible computations that can happen from one state to another and belong to one block. It will be designed to check that all possible computations between two blocks commute and existence of a cancelling words between two blocks. These two operations can be checked in p time. For each weak dependent class, on seeing every new context, to verify k-scope bound, we need to store only the previous k context of that class. We use this fact to construct a reachability graph whose nodes are all the possible configurations of the k context for every weak dependent class, and whose transition add a context to one of the classes, remove an empty context after cancelling blocks non-deterministically. Finally, we show that the reachability in this graph is equivalent to our decision problem and it is in p-space. Now we look at block decomposition. If W can be reduced to empty, then there is a reduction that swaps and cancels letters. We can define a similar notion that swaps and cancels blocks or infixes in one step. Let W1 to Wm be a reduction of W into blocks. If W can be reduced to empty by blockwise operations, we call it freely reducible. Such a block decomposition always exists for an acceptable word. Since the letter by letter decomposition is a trivial one, we will usually take a coarser decomposition. We note that blocks are maximal in nature. Now we show the upper bound on the number of blocks in each context. For a k-scope bounded word with irreducible context, which is obtained at the end of saturation part of greedy reduction, there is a freely reducible block decomposition where each context is broken into at most 2k blocks. It can be intuitively understood from these two facts. First, blocks of each context can only cancel with blocks of their own weak dependent class that are at most k context ahead or behind. Second, for irreducible context, at most one block from a context can cancel with the block of another context. This is because more than one block would either require the blocks are side by side, which contradicts the maximality of blocks, or it would have to commute with a dependent symbol, which is not possible. This gives us a bound on how much information we have to store. Now we move from words to valence system itself. To compactly represent all possible computations in a block, we use block abstractions. A block abstraction can represent all words U hat such that there is a word U which satisfies the following. U reduces to U hat. U is read on some path from start to the end state. U begins with the symbol F. U contains the symbol O. The set of vertices B occurring in U is a dependent set. The maximal elements of B is a subset of Umax, and the minimal elements of B hat corresponding to U hat is the subset of Umin, where Umax and Umin are the neighbor antichains derived from some set U. This construction ensures that the following two operations occur in P time. Checking if all computations in two block abstractions commute by checking the independence of the minimal labor antichain. Checking if there is a computation U1 in block 1 and U2 in block 2 such that U1 U2 reduces to empty. This is done by first saturation of the two block valence automata and then concatenate them and run a PDA to check empty stack. Context abstraction is simply a collection of block abstraction. The first symbol of the context is the first symbol of its first block, and an appearing symbol can be selected from any of the appearing symbols in the block. Now we look at the overall description of the reachability graph. The vertices of the graph contain the current state in the valence system, the weak dependent class into which the last context was added, and for each of the weak dependent class, its last k context abstractions. The edge in the graph exists between two vertices if and only if there is some weak dependent class, some context abstraction, and some sequence of block reduction after inserting the context to the weak dependence class such that the result vertex is the next vertex. In this graph, we start from a state with all contexts empty and valence system start state, and we want to reach all contexts empty and valence system end state. Now, by a worst case calculation, one can observe that the size of the reachability graph is an exponential function of polynomial terms of k and the number of symbols in the graph monoid. Thus, our problem is reduced to reachability in an exponential graph, which is known to be in NL, so the reachability is in p space in k and the number of symbols. Hardness can be obtained by considering the case when the graph storage is multi-pushdowns. More elaborate methods to obtain hardness for this case and for special cases are covered in the paper. In conclusion, we describe our approach to show a p-space bound for scope-bounded reachability in valence system, along with other results by constraining the scope bound and the class of graphs which can be derived from the main result. Thank you.
Thank you for the nice presentation, Anish. Now is the time for questions. So we don't have anything ready yet, but feel free to type in anything now. So I will ask a question meanwhile. So you ask for the reachability problem, like a coverability problem, right? Like you want to reach the control state and you don't care what is the word on the graph monoid once the target configuration is reached. But if you describe it in, if you give a specific word, for example, to be the target the word on the of the graph monoid, how does it make it more difficult, or instead of a single word, maybe if you're giving describing it using some regular set, for example, would that would that go through still with your?
So perhaps I can answer this. I believe all the upper bounds are for the configuration reachability, and all the lower bounds are for state reachability, so that the complexity will always be the same. If I'm not missing anything, I think this all they all coincide.
Okay, thank you.
So I think in the paper we have the configuration reachability. So you have to reach the element has to be the neutral element. So you have to reach so this is equivalent to the configuration reachability problem. But I believe all the lower bounds also work for the state reachability problem, so that they should all coincide.
So what is the minimum dependency graph, or the I think you call it gamma, the dependency that you have on this graph for the graph monoid? What is the minimum structure that you would need for the lower bounds to hold?
So we considered several situations. So in the most general case where the scope bound is part of the input, you would just need two VAS counters. So if you have, or just two counters that can commute, then you already have a p-space lower bound. In the case with a fixed scope bound and a fixed graph, I don't remember. I have to look into the paper. One sec. Ah, all right. Then it's always in polynomial time. So if the scope bound is fixed, then it's always either in NL complete or P complete. So then the complexity drops considerably.
Okay. Thank
Then it
you.
only depends on whether the graph is a clique or not. So if it's a clique, then it's NL complete, and otherwise it's P complete.
Okay, thanks a lot. So I don't see any questions coming up, and considering the fact that we are already 5 minutes beyond the end of the session, I propose to stop the session now, conclude the session now, and we will meet for the next session after a 25-minute break. So we meet at the normal time at 3:45 European time. So thank you again. Thank you all the speakers and the panelists, and thank you all for attending.
Thank you.
Thanks. Bye.